Welcome. Next, we are going to look at how to deal with situations where there is more than one constraint when we use the method of Lagrange multipliers. The answer is simply that you use one new multiplier for each equation. So you form the auxiliary function by taking the objective function, then minus lambda 1 times left-hand side of the first equation minus lambda 2 times left-hand side of the second equation, so on, where lambda 1, lambda 2, etc. are the new variables, the Lagrange multipliers. To illustrate this, let's write down the equations for the critical points of x squared plus y squared plus z squared, subject to the condition x plus y plus z equals 6 and x, y, z equals 8. We'll start by first writing the equations in the form something equals 0. So subtract 6 from both sides of the first equation and subtract 8 from both sides of the second equation. So the equations become x plus y plus z minus 6 equals 0 and x, y, z minus 8 equals 0. We will form the auxiliary function. Take the function whose critical points I'm trying to find, x squared plus y squared plus z squared, minus lambda 1 times left-hand side of the first equation in the rewritten form. So minus lambda 1 times the quantity x plus y plus z minus 6 minus lambda 2 times left-hand side of the second equation. So minus lambda 2 times x, y, z minus 8. That's the auxiliary function because we have only two equations. Now we'll find the equations for the critical points. So take the partial derivatives with respect to the original variables x, y, and z. So let's find the partial derivative of the auxiliary function with respect to x. Remember that we'll be treating y, z, lambda 1, and lambda 2 as constants. The first term is x squared, its partial derivative with respect to x is 2x. The second term is y squared, it does not have an x in it, so the partial derivative is 0. Same goes for the third term, z squared. And then minus lambda 1 times something. So minus lambda 1 is a constant factor, then it stays as it is. And then I differentiate the inside with respect to x, which gives me 1 plus 0 minus 0, or just 1. So I just get lambda 1 times 1, or just lambda 1. And then in the last portion, I have minus lambda 2, which is again like a constant factor. So it stays as it is. Then I differentiate what's inside. I have x times y times z. It's like x times a constant factor, so derivative with respect to x is 1 times a constant factor. So I get 1 times y times z minus 0, or just yz. So our first equation is that 2x minus lambda 1 minus lambda 2 yz equals 0. Again, we can get the partial derivatives with respect to y and z by symmetry, or we can go through the calculations again. The partial derivative with respect to y will be 0 plus 2y plus 0 minus lambda 1 times the quantity 0 plus 1 plus 0 or just 1, so minus lambda 1, minus lambda 2 times x times 1 times z minus 0, or just xz. The partial derivative with respect to z will be 0 plus 2z minus lambda 1 times 0 plus 1 minus 0, or just 1, minus lambda 2 times the quantity x times y times 1 minus 0, or just xy. Just as in the case of one equation, the partial derivatives with respect to the Lagrange multipliers will be just the negatives of the left-hand sides of the rewritten equations, which means they give equations which are equivalent to the original equations. So instead of doing partial derivatives with respect to Lagrange multipliers, we can just use the two original equations, x plus y plus z equals 6 and x, y, z equals 8.